So after some background information on machine learning, now let's look at how we can implement this machine learning workflow with the validation set approach in R and in the tidyverse. The tidyverse, or specifically tibbles, have one advantage, and that is that tibbles can store arbitrarily complex objects in columns, in so-called list columns. And what this means is that instead of just having a single data point in a column in each observation, we could instead, for each observation, have something very complex like a model output, or we can even save an entire data set for a specific observation. And for example, we can nest data sets. Using the nest function, we can kind of split our data set into subsets and then collapse it by certain groups. So let's look at an example. We have this Gapminder data set that contains, for 142 countries, several observations over different years, and then it contains like life expectancy, population, income, and so on. And what we can do now is we can collapse this data set on the country level and then save all the data for that country in a single observation. So the way to do this is we create a new data set called Gapminder nested. And then we use pipe to feed the Gapminder data into group by country. And then we feed this into nest. And now if we look at this nest data set, we can see we only have 142 observations left from 1,700 and only 2 variables. And one of the variables is, of course, the country by which we grouped. And the other one is just the data. So now we have just for each country, it's now one observation, and the data column for that country just contains the entire data set if we had filtered it by that country. And you can see how this is useful if you want to estimate the same model for each group separately. You can now just map over each element in the data column and estimate the same model. So if you think back to the last assignment where you had to estimate the same model for each of 5 different US congresses, you could, using this approach, you could just collapse the data by congress and then map the same model over the data elements for each of the congress. So now let's use this. We now want to run a regression of life expectancy on GDP, but we want to run this regression separately for each country. Now that we have already collapsed the data into so by country, we can now just use map to kind of create a new column. Like we use the assignment pipe to feed Gapminder nested into mutate, where we create a new column model, and the object in model is just the model life expectancy on GDP applied to the data object for each country. And now if you just look at this, if you take Gapminder nested and the model column, and we look at the first element from the model column, we can now see that this is a regression output object. And we can now go a step further. So now that we have a data set that contains the country, it contains the data for each country in each row, and then it contains the model output for each country. We can now kind of extract all the diagnostics from each model from each country. So we can use the Broom library that you've already seen with the tidy function, but we can use some of the other functions that Broom provides as well. For example, glance lets us extract model diagnostics from each model, or augment allows us to extract fitted values from the model. So what I'm doing now is I'm going to create an additional variable in the Gapminder nested dataset where I extract the R squared from each model that we estimated on each country. So I again use mutate. I create this new variable r squared, and then I map glance where I extract the r squared over the model column in the nested data set. And notice here that this is an anonymous function, and the dot x is simply a placeholder that tells us use the object from the model column inside here, inside the glance function, then just extract the r squared. Yes. So now after we're done with this, we now have a country column. We have for each country the data. We have the model estimated in each country, and then separately we have the r squared in for each country. And we can now go scroll through the 142 countries and easily observe what is the r squared of this model that we ran here. So the reason why this is very useful for machine learning is because when we talk about when we use resampling methods, we split the data into a lot of different testing and training data sets. And we want to estimate the same model for each of these data sets. So you can imagine how it's very useful if we can just save all of these data sets as observations in a column, and then just easily map an entire model over each of these data objects. So I'm going to show you an example from using the vehicles data set, where we try to explain the miles per gallon by using some engine specifications. And we're going to use the R sample package, which allows us to split the data into a lot of different training and testing data sets. So first, we will need an initial split. We just want to take the testing data set out of this, right? And if you remember, the testing data is going to be left completely out and will not be part of the model selection part. And once we have the training data set, we're going to split it into these subcomponents where we always leave one out to evaluate the model. So here we perform the initial split. We say we want to have proportion 3/4 should be training and 1/4 should be the testing data. And then we can extract from this split object the training and the testing data. And if you want to check the dimensions, you can see here it's indeed 3/4 and 1/4 of the data set. Now, to perform cross-validation, we need to make this very complex split. That, for example, if we want to have it 5-fold, we need in each iteration split it into 5 components, keep one of them out as a validation set and 4 of them as the training. But luckily, our sample package gives us the vfold CV function, which simply splits the data set into these training and testing data sets. So if we now create a new data set called CV split, we give it the training data set and we say we want to have 5 splits. And the results of this will be a data set that has simply 2 variables. It has an ID, and then it has a split for each fold. And what the split contains is it contains the training data set and the validation data set. And we can then extract this from the split. Also notice that I set a seed here. And what this means is that since resampling methods, they randomly draw, we want to set a seed so that the resampling methods, every time we run it, draws exactly the same random numbers. And setting a seed allows you to do that because the algorithms that draws random numbers, it usually starts with a seed, which is an input number, and then it performs a very complex calculation. At the end of that, something pops out that looks almost random. And if we use the same seed every time, we will get the same random number every time, and therefore we can easily reproduce it. So whenever you do something that involves random sampling, such as Monte Carlo simulation or resampling method, it's good practice to always set a seed. Okay, so now let's continue with split here. So now we see we have this split, which, as I already said, contains the training and testing data set. Now we can use map to extract the training and the testing data set. So now we create a new column CB train and a new column CB validate. And for CB train, we simply extract the training data set from each of the 5 splits. And for validate, we extract the testing data set from each of the 5 splits. And now our data set has 4 variables. It contains the split, the ID, the training data set from each of these splits, and the testing data set from each of these splits. So now we have a data set that contains like all of this here. So for each split, we now have the training one, which is all of these green ones combined, and the blue one is the testing one that is separate. So now we can see how the approach that we discussed earlier, where we just map over different data sets that are stored in a column, it becomes in very handy here. Because now what we want to do is we just want to estimate the same model on each of these training data sets and then validate it on the validation data sets. And validate means we just try to predict how well, we just try to predict the outcomes from the validation data set, and then we use a measure to measure how well this model performs in terms of prediction accuracy. So to build and evaluate a model, we need like 3 components. So first of all, we need the true fuel consumption for each of the vehicles. That's going to be the true value against which we're going to compare our prediction. Then we need the predictions of fuel consumption from each model, and we need a metric to evaluate the error of the prediction. So the first step is we need to estimate the simple model. And here we just estimate the miles per gallon, which is the highway miles per gallon, on a model that has the cylinder and the displacement of the engine. And we map this over all the training data. So it means that for each of the training data sets in our table, we're now going to apply this model here. And we save this as a new column model. Then in a second step, we're going to use the model that we estimated and take the testing data and then predict from the testing data using the model the miles per gallon. So since the usual map function only allows for 1 input, but we need 2 inputs. We need the model that contains the coefficients, and we need the testing data, which gives us the covariates that we use to predict the miles per gallon. So we need 2 inputs, and luckily there is a function called map2, which simply takes 2 inputs and then a function that also uses 2 inputs. So now we create a new column that is the true miles per gallon, where we just extract the true miles per gallon from the validation data set, and then we create a prediction column where we just predict the miles per gallon from the engine specifications that we see in the testing data. Once we have this, now we can simply evaluate how much are the predictions off from the true miles per gallon estimates. And to do this, we need a metric, and there's like 2 commonly used ones. There's the root mean squared error, which is simply the sum of all the squared deviation between the true value and the predicted value, and the mean absolute error, which is simply the average of the absolute deviation of the true value from the predicted error. And the mean absolute error gives us just an estimate of, on average, how wrong is our prediction in absolute terms. So this is the one we're going to use here. We're now going to use the true miles per gallon and the predicted miles per gallon. And then we just calculate the mean absolute error, which is this metric here, add this as an extra column in our data set. And now for each of these 5 models, we can now see how much our predictions are off on average. And we see that for each of these 3 models, the prediction is off by about 3 miles per gallon. And it's actually very consistent, so which means that this model is probably very, it's not picking up, it's not clearly not overfitting, because it's very consistent in how wrong it is. Okay, so now we have created a full machine learning workflow where we have started with splitting the data, extracting the training and the testing data, using the training data to estimate a model, and then predicting the values and comparing this to the 2 values from the validation data set. Now, we can, of course, try to improve the model. Let's add an additional covariate, which is a covariate for the year as a factor variable. And now we just do the same as before. We use the cross-validation data. We estimate a model on the training data. We predict data by using the model and the engine specification from the testing data. And then we compare the model predictions of in the testing model to the true miles per gallon data in the testing data set. And we can then look at the mean absolute error again of this new model. And now we see it's about 2.65 or 2.7. Again, it is very consistent. It's not, doesn't seem to pick up a lot of noise. And we see that adding this additional year covariate has reduced the prediction errors quite a bit. And we're now only off by about 2.7 miles per gallon on average.